Okay, guys, moving on a little bit. We just looked at the band of stability, and we looked at how and why why nuclei are unstable. And again, we're thinking about the alpha radiation, the beta particles, and the positrons as a way the nucleus can become more stable by emitting this energy of these particles, and why that's the case. The next step, what we want to do is look at how we write the equations for this and how we can put this together in some type of way that we can write it. So we looked at something called natural decay or natural decay equations. And what you want to look at is you want to look at this table, a special table N. And this table is in the reference table. And you can get an idea about the type of decay mode by looking here at this line here. Again, a nuclide is a radioactive nucleus, so that would be listed here. The name of that nuclide is here. Okay, and the decay mode is what particle that gives off, and we want to be able to write an equation for this. All right, so just understand a couple of things. We're going to follow the form A plus B plus a particle. Okay, and just so you know what this really means is that you're going to start off with A, which is your unstable nucleus. That's going to decay to another nucleus, some type of particle, and this is going to be your radiation. So your radiation is actually going to be emitted. Emitted means to be given off. So this is going to be given off by the nucleus, and that's the radiation. So what we want to do is natural decay, which is something that happens naturally without humans being involved in this. This takes place on its own. Okay, and this is a spontaneous process. Okay, that happens on its own. Okay, so that's what we want to do with this kind of thing. All right, how we actually balance these, they got to be balanced. So we're going to balance the mass numbers. So the sum of the mass numbers must be equal across the arrow. Okay, so you're going to think of this arrow as an equal sign. The sum of the mass numbers must be equal on both sides of this equation. And the sum of the atomic numbers must be equal across the arrow. So that's important to know that you're thinking of the arrow as your equal sign. And again, there's a few ways you can look at this. I like to use a certain way. If you want to use your own way, that's good too. Okay. And again, if you need to find the decay mode, if it's not given to you, again, you have to know that you need to use the table for it. Sometimes a question won't tell you this. So for example, let's just say I have thorium-9. The easiest way that this is given is typically they will give you a nucleus, say thorium-230, and again, the atomic number would be 90, and they're telling you that it's giving off an alpha particle. Again, this would be alpha decay, this little circle here. Now again, down here, thorium-230 may or may not be on the chart, but they are telling you it's giving off an alpha particle. And again, the particles sometimes can be written before the B or after the B. So these can be written, backwards. That's fine too. You just have to realize that that can happen. So really, you're thinking of this being the equal sign. All right. So I like to say, this is me. You can either do this two ways. You can either say 230 minus 4, okay, is 226, or you can say what number plus 4 is 230. So you could say what number plus 4 is 240, or you can say 230 minus 4 is 226, because you're thinking of this being the plus sign. So 226 plus the 4 is 230, okay? And I like to think of what number plus 2 is 92, and I think of that being, and of 90 is 88, okay? And if I look this up, this would be radium in that case. All right, so that would continue. And then again, you may want to check this at the end. So 88 plus 2 is 90, okay, and 226 plus 230, plus 4 is 230. Now, just to understand, too, that this sometimes, in reality, 88, again, would decay once again. So you could literally write another formula for this. You can say 226, 88, and then put another arrow, again, and do another decay. Of course, you'd have to know what particle it was. They would tell you that, but that's called a decay series. So a decay series is when you do this repeated steps to get stable. Okay, in this case, they were only asking you about the missing particle. Now, this can be done another way. And example number 2 is another way you can do this is give you nothing. They can say, okay, phosphorus 32, and just give you an arrow. And of course, that's not helping you because they're not giving you any other information. But then you would have to know to take this and look it up in the chart and look down here at phosphorus 32 and realize you're giving off a beta particle. So then you can write the formula for a beta particle would be E with a -1, okay, and some other particle. Now, don't fall into something I call the beta particle trap. And the beta particle trap is, I know what you're thinking. You're thinking 14 right here. But just be really careful because remember, this is the equal sign. So you want to say what number minus 1 is 15. So in fact, you'd have to put 16 here, not 14. That's a big mistake people make a lot of times. Okay, and again, this is easy. What number plus 0 is 32? So this is 32. And again, that would be sulfur. Okay, in that case. The sulfur is 16. Okay, so that would be right. So again, you want to double check. 32 plus 0 is 32, and 16 minus 1 is 15. Okay, again, you could go 32 minus 0 is 32, or you can go 15 minus a minus 1. Again, minus a minus 1 would be a positive, and that would give you 16. So either way you want to do this. So again, this example number 1, I think, is the easiest. Example number 2 is, of course, taking a little more information away. And example number 3 is another way they can ask a natural decay equation is just ask you to write the whole thing from scratch, from the beginning. Okay, in this case, they're just saying write the decay equation for carbon-14 and giving you nothing. So again, how do you start this? If they're saying the decay of, they're not telling you what's decaying, so you would start it by writing carbon-14 and the atomic number 6, okay? Then putting your arrow, again, because you're going to follow this form for a natural decay, okay? And then going to here and looking all the way up here, finding carbon-14 and looking at a beta particle. Again, right, this is a beta particle. So we would write the beta particle, okay? And we would say 14 minus 0, what number plus 0 is 14? I would say 14. And I would say what number minus 1 is 6? And that would be 7, because 7 minus 1 is 6. Okay, and I would look up on my periodic table, I would find that would be nitrogen. All right, so 3 different ways they could ask this. Again, with increasing difficulty, I think. Again, and this is not hard. It's just increasingly less information they're giving you to do a natural decay. All right, so that would do it on natural decay. For artificial, you can also do this artificially. And artificial radioactivity is slightly different. Okay, and we go back to the 1920s when Rutherford, yes, our friend Rutherford with the gold foil experiment, was playing around with radioactive materials, okay, and he did some work with this. And Rutherford got this idea to fire alpha particles. Okay, again, it was your helium nuclei with the 4 and the 2. You got the idea to take this and fire it at nitrogen atoms, okay? And what he discovered is that he was getting oxygen out of this and some protons, which of course are hydrogen atoms, okay, or hydrogen nuclei. Okay, and this was actually the first time that someone had induced or forced an atom to change its identity or change itself into another element. Okay, and we call that artificial radioactivity or artificial transmutation. Again, artificial means by man, transmutation means changing an element. So what he actually did was this. He took nitrogen, okay, and instead of in natural decay, it's happening on its own, like this. Remember, we did that before with a particle. This time we're taking a particle and we're firing it at a nucleus, okay? And that produced this. So really, you have this reaction that is using the same idea where keeping the atomic numbers equal and the mass numbers equal. It's just you're going to have multiple particles on each side. So if you have 2 particles on this side, in this way, versus only 1, then you have an artificial transmutation, artificial radioactivity. Now, what you get as a result on this is going to be different, okay, because you don't really know what you're going to get. Okay, again, several things can happen when you crash 2 particles together. Okay, you could get a sticking together, okay, of the particles, or you can get a breakdown. All right, and again, you'll see as we move on, these can both be true, but they can either stick together and mush together and form something new, or you can actually break down that particle. So again, this is intense research. Again, without a real mystery on what we're going to get. But again, scientists do stumble on some patterns from time to time. Okay, a couple of little words here. You want to call this. This is going to be sometimes called the target nucleus. Okay, and this is sometimes called the bullet. Okay, and sometimes these are called daughters. Okay, daughter nuclei. Just a couple little vocabulary words that you may see along the way. And again, the bullet is fired at the target, right? So again, scientists choose what bullet they're going to use and what target they're going to use, and then they study the pieces that jump off here. Okay, so that's what happens. Okay, so again, what's the idea behind artificial? New elements can be man-made when they do this, right? So if A combines with the bullet and then they stick, then you create larger elements. So atomic numbers 93 to 118 were created this way. Okay, and this is still occurring. These are very unstable elements at this point. We really don't have much of a use for them, and their half-lives and their existence are really short. But nonetheless, we make new elements. Okay, and again, how do we do this? We use a special machine called a particle accelerator. Okay, and again, without going through too much of an explanation, basically what we do is we have this source of protons or a source of something, and when we have these big magnets, these Ds are really magnets. They call them Ds, but they're really magnets. Okay, and what they do is they're flung around at high speeds. Okay, so really this is accelerated. We call it accelerated because you're accelerating this, and again, protons are positive. So what we can do is we can ionize them, get the positive charges, get them swinging around like you would swing around, a key on a chain. You just swing that, okay, at high speeds. And then what we would do is then put a nucleus right in the path of that. So as this swings around at high speed, you get this high-speed proton coming around, and boom, you'd crash this into a big collision here. All right, and that would allow us to study all the pieces that are a result of this big collision. I like to use an analogy of like a race car flying around a track, and then you go out and you put a pumpkin in the middle of the track, and you allow that car to impact the pumpkin at a really high speed. And of course, that pumpkin can either stick to the car and make a larger car with a pumpkin, or you could actually obliterate the pumpkin into a billion pieces and then study what's inside that pumpkin. So that's what scientists like to do. So particles are accelerated at high speeds. They're allowed to impact other target nuclei, and then scientists simply just study those atomic collisions and see what things are made of. And a lot of data about atoms has been collected about this, and then some interesting information about the nucleus has been discovered this way. All right, so that's artificial radioactivity. How you would handle the problems is very similar. Again, 14 plus the 4 is going to equal the 16 plus the 1. Okay. Which is really, this should be 17 here. Sorry, that's a mistake. 17. Okay, so 17 plus the 1 would equal the 18 here. Okay, where this would also equal 18. So that would be 17. That's a little typo there. So that would be an 18. And again, the 8 plus the 1 would be 9 on the bottom, and the 7 plus the 2 would be 9 on the bottom. And that's how you would equalize this. Again, they will give you everything except for 1. You just have to notice what kind of reaction you have here. All right, this is CERN. This is a particle accelerator that's actually in Switzerland and France. It's actually built underground. And this is like a mile or so in a big circle here. And this actually winds particles around in this huge big thing. There's a multinational experiments going on in this huge reactor. Okay? And this would be the inside. This would be the accelerator right here. And you can see this is one of the workers in the big tube where he's monitoring all these big magnets and all the machinery that goes along with this very high-end equipment doing this. All right. So that ends the show on this one. Next, what we'll look at is the types of artificial radioactivity, and we'll look at nuclear reactors. We'll look at atomic bombs. We'll look at the way that we can use this artificial radioactivity for good things and bad. All right. In the meantime, we'll see you then.